In the previous lectures, we discussed about the behavior of the resistance, behavior of the capacitance, and behavior of the inductance individually in the circuit. Today, we will explain what is the LCR circuit, series LCR circuit, and how to calculate or how to say what is the phase angle between the current and the EMF in a series LCR circuit. In a series LCR circuit, as the name suggests, we have got a series connection of resistance, inductance, and capacitance connected to an AC source of EMF E is equal to E0 sine omega t. Now, we know that the phase difference of the current and the EMF in resistance is 0. That is depicted by the ER in the same direction and IR in the same direction. In L, the inductor, the current lags behind the voltage by a phase angle of 90 degree, and in the capacitor, current leads the voltage by a phase angle of 90 degree. So here IL is this way, EL is perpendicular but anti-clockwise direction. Here EC is perpendicular but clockwise direction. The clockwise direction means lag and the anti-clockwise direction means lead. Now, if you look at the phasor diagrams, if we take the current is this way, so voltage across the resistor is along that way because the phase difference is 0. Now, across the inductor, it leads the current by a phase angle of 90 degrees, so we are having this VL, and here we are having this VC because the voltage across the capacitor lags behind the current by a phase angle of 90 degrees. Now, if we take the inductive reactance is greater than capacitive reactance XC, that means voltage across the inductor will be more than the voltage across the capacitor. So we will be having this much equal to VL minus VC. Let's complete this triangle. So this much will be equal to VL minus VC, and let us complete this triangle. So this side, if it is O, it is A, it is B. By Pythagoras theorem, hypotenuse square is equal to base square plus perpendicular square. Now H square, it is the resultant voltage across the resistance, inductor, and capacitor in series. Let it be equal to Vz. So Vz square is equal to base square is VR square plus perpendicular is VL minus VC whole square. So Vz square is equal to root of VR square plus VL minus VC whole square. Now, as it is a series circuit, so the same current flows through R, L as well as the C, so current is the same. So we know that from the Ohm's law that voltage across R is the multiple of current through R and the resistance R. Similarly, through L it is the multiple of current and the inductive reactance, and through C it is the multiple of the current and the capacitive reactance. But in this case, series LCR circuit, as the current is the same current flows in R, L and C. If we take combined resistance of R and reactance of L and C in combination, we call that as impedance, and that impedance is shown by letter Z. Let the combined impedance be equal to Z, as the same current flows, that is I, through that Z. That means the voltage across, combined voltage across R, L and C will be equal to the product of the current and that impedance as per the Ohm's law. So we will be having this Vz will be equal to root of VR square plus VL minus VC whole square. That will be equal to I into Z, where Z is the impedance, that is root of I square R square plus I square will be common into XL minus XC whole square. Taking I square out of the root, it becomes I. That means we have got IZ is equal to I into root of R square plus XL minus XC whole square. I and I goes. So we have got the impedance Z is equal to root of R square plus XL minus XC whole square. This is the resultant impedance of the series LCR circuit. Now, if we have this voltage across R, L and C makes an angle of phi with the current or with the voltage across the resistor, that is VR. That means the phase difference will be phi. And from this triangle we have that tan phi is perpendicular by base, that is XL minus XC divided by R, or phi will be equal to tan inverse XL minus XC divided by R. This will be our phase difference, that is phi is equal to tan inverse XL minus XC divided by R, where XL and XC are the reactances, combined reactance, and R is the resistance of the resistor. Let us talk about the special cases. Case number 1 is when capacitive reactance is equal to inductive reactance, that is XL is equal to XC. In that case, our impedance will be equal to root of R square plus XL minus XC whole square, as XL is equal to XC. So this quantity XL minus XC becomes 0, so Z will be equal to root of R square, so Z is equal to R. In this case, the phase difference will be equal to 0. That means the overall impedance of a series LCR circuit, when the capacitive reactance is equal to the inductive reactance, that circuit's impedance is equal to the resistance. That means we are having not the effect of the reactances, either inductive or capacitive, so that circuit is called as non-inductive. When Z equals to R, that circuit is called as non-inductive. Case number 2. If XL is greater than XC, that means the capacitive reactance is less than inductive reactance, or inductive reactance. In that case, XL minus XC is greater than 0. This circuit is called as inductance dominated circuit. Inductance dominated circuit. In case number 3, if XL is less than XC or XC is greater than XL, in that case XL minus XC is less than 0. That means XL minus XC is negative. That circuit is called as capacitance dominated circuit. So when we have capacitive reactance equal to inductive reactance, in that case our series LCR circuit is non-inductive. That means Z is equal to R. If XL is greater than XC, in that case XL minus XC is positive. That means the circuit is inductance dominated. If XC is greater than XL, in that case XL minus XC is negative, and that circuit is capacitance dominated. Thank you.